LT6 multiplying probabilities. Here we go. Probabilities involving single stage experiments are easy enough because only one thing is happening to affect the probability. You flip a coin once, you pick one person at random, or you pull one card out of a deck. Probabilities, both empirical and theoretical, become increasingly more complicated with multi-step experiences, which more than one thing happens. Flip a coin 3 different times. How we can handle these types of probabilities actually comes from the conditional probability formula. Given the probability of an event B occurring given A has occurred, answer the following. Rewrite this formula, solving for P of A and B. So remember, to get the top part by itself, I get rid of dividing by the P of A by multiplying both sides by P of A. Boom, there it is. How could you rewrite this formula to be if they're independent? So if one has nothing to do with the other, then P of B given A doesn't really matter. You can just multiply that by the P of B. Okay, those are just kind of using your formulas. Pause the video if you need to. Okay. This rearrangement of the conditional probability formula gives us a useful tool for calculating the probability that an event occurs in multi-stage experiments. You will easily be able to accomplish this if you systematically phrase the question as intersection of events connected by the and. Consider the spinner below. The spinner is spun twice and the results are recorded. Are the outcomes of the 2 spins dependent or independent? Well, they're definitely independent because what we can get on the first spin does not change the probability of what we get on the second spin. It doesn't matter. B, what is the probability that you will get an even on the first spin and a number greater than 5 on the second spin? So to figure that out, because they're independent, we can just multiply these 2 probabilities together. Probability of E and greater than 5 means that I can take the probability of getting an even times the probability of getting a number greater than 5, and that will be the same. So picking an even is 4 out of 8 of the numbers. Picking a number greater than 5 is 3 out of 8. Because remember, 6, 7, 8, boom. Multiply those 2 percentage, you get 3/16. Okay. C goes to a different slide, but I'm going to read it. What is the probability that you will, if you need to pause the video and write those down, do so now. What is the probability that you will spin a prime number and a perfect square in either order? Note that this is a little more complicated. So there's 2 situations. You could first pick a prime, then roll a perfect square, spin, excuse me, or you can get a perfect square first and then a prime number. So let's figure out these 2 different probabilities and then add them up, okay? So prime number and perfect square. So prime numbers, we've went through this. There are 2, 3, 5, and 7. So those 4 out of 8 prime numbers. How many of these are perfect squares? Well, only 1 and 4 are, so that's 2 out of 8. So first picking a prime would be 4 out of 8 times 2 out of 8. 8/64, 1/8. And then going in the other direction, I know it seems simple, but it's going to be the same probability, but we still have to account for both of them because one's different than the other a little bit. So then we just take those 2 probabilities and add them up. What's the probability of this or this is adding those 2 together because you can get this or this. So that both happen, so that's why you add them up. Pause the video if you need to write any of that down. As experiments grow more complicated with stages, theoretical probability becomes increasingly more complicated. It's especially important to note whether you're sampling with or without. So a class consists of 12 girls and 8 boys. A group of 3 is picked to give a speech. If the students are picked at random, what's the probability that it will all be boys? Use the events below to show how you calculate your answer. So E of 1 is the event that the first boy is picked. E of 2 is the event the second boy is picked. And E of 3 is the third boy is picked. Okay? So we're trying to figure out this probability. Here is the formula that gets rather bit distracting, but hopefully it kind of makes sense when you start using the fractions. So picking a first boy would be 8 out of the 20. Okay? But then if you think about it, if that boy goes, you can't count him again. So you have 1 less boy and 1 less total. So the next probability is just going to be 7 out of 19. Okay, that boy goes. Now we have 2 less boys, another less boy. So we end up with 6/18. Multiplying those probabilities together, we end up with a 5% chance that you're going to get boys on each 3 picks. Multiplying probabilities together and just kind of thinking about whether you're placing them back in or not. Pause the video if you need to write any of that down. Say that the power generating facility has 3 primary safety switches in case of emergency. The probability that one of these switches would fail is 5%. What is the probability all three will fail given that the switches are independent of one another? Okay, so they're independent. So what's the probability that the first one will fail, the second one will fail, the third one will fail? Well, they all have a 5% chance of failing. So I just got to take and multiply those 5% 3 times, leaving us with a very comfortable 0.0125% chance of those not failing, of all three of them failing. Which is kind of nice when you think of it. I mean, hopefully none of them fail. 5% is a low percent, but multiply the probabilities together. Here we go. Many times when using multiplication rule, we need to be careful about how we frame the question. But if we properly frame it with and or, then the rules of the probability will work out. A company was determining the effectiveness of its warranty sales on computers. They took data on the number of customers who purchased warranties on 2 different brands of computers. And if the customer was chosen at random, what's the probability they did not purchase a warranty? So if we look at our table, we have type 1 computer, type 2 computer, and then we have percent of customers purchasing, and then those that purchased and did the warranty. Okay. The event here is quite complex. We need to find the probability someone bought type 1 and didn't get the warranty, or bought type 2 and didn't get the warranty. And again, we don't have the data on this chart of those that didn't get the warranty, but we can kind of use the 100% minus 1 situation. So here we go. Okay. It all pops up at once. I forgot to fix the animation. So what's the probability of taking type 1 and it has no warranty? Well, type 1 computers was 68%. Okay. Now, the 65%, where does that come from? Well, if you take 100% and subtract the 35% of those that did get the warranty, that means the 65% didn't get the warranty. So multiplying those two percentages together, you get 0.442. Great. Now let's do type 2. Again, how many people got type 2? 32%. Of those, how many did not get the warranty? So 100 minus the 56 gives you the 44. So that's where those two values come from. Multiply those two together, you get that decimal. Now we just have to take those two multiplications and add them up, one or the other. You end up with a 58% chance. So what's the percent they did not purchase a warranty? We had a 58% chance of not purchasing the warranty. And there's the last lesson for probability. Hope all's well.